Well, thanks everyone for making it back in after the break. I'm going to talk about LCROSS, and I really wanted to gear this talk towards the students that are in the audience, because I know that the Lunar Science Institute has made a great stride to try and bring students in, and we need that to keep this community going. So we'll give you some background about the mission and then also what we're learning and where we're going. And I want to give credit also to the rest of the LCROSS Science team and also the LCROSS PI, Tony Colaprete, who all helped contribute to the science we're going to talk about today. So I was asked to give this talk, the LCROSS Revolution, and I did not come up with the title. I can't take credit for that. But I thought to myself when I was starting, so what exactly is a revolution that I should be talking about? And Merriam-Webster says it's a fundamental change in the way of thinking about or visualizing something or a change of paradigm. And so what we want to talk about today is how this one case study of this LCROSS mission really was that. And particularly for the students to capitalize on what Clive said earlier, I think, that lunar science is still active, it's vibrant, it's hands-on, it's something that you can contribute to and make meaningful contributions to the community. And hopefully, with the work, the groundwork that's being laid and the vision that was laid out earlier this morning, there will be more mission opportunities for everyone to get involved with as well. So for those that aren't familiar, just very briefly, LCROSS is the Lunar Crater Observation and Sensing Satellite. We launched June 18th of 2009, and this is the actual launch down in Florida. We launched with the Lunar Reconnaissance Orbiter, so you get those two spacecraft on the one launch vehicle. And then we impacted in the Cabeus crater that you heard about this morning. Here's a thermal infrared image from the LCROSS shepherding spacecraft going in, and here's the little dot showing in the permanently shadowed region, that's where LCROSS actually hit. The whole point of LCROSS was to test whether or not there are water ice deposits on the moon. Very simple, very basic question, level 0 question that we actually didn't have a definitive answer to. And so with this very focused question, that's how the whole mission was organized. And so what we did is we impacted into Cabeus, kicked up a plume of dust, debris, ice, whatnot, and analyzed what was in that plume to find out what was actually sequestered in that permanently shadowed region. So why we did this, and the best ambassador for this message is Mike Wargo, and he already said it this morning, so I won't dwell on this, but the value to both science and to exploration. There are obviously a tremendous list of science questions. I've just listed a few up here that were addressed by the LCROSS mission, and also for exploration. And in a book edited by Wendell Mendel, there is no way other than spacecraft exploration to ascertain whether or not useful quantities of such polar ices are present. If they are, they will provide an overwhelming reason for locating at least some part of a base complex near a pole. So the answer to the question, is there water ice or is there not, is incredibly important as we look at the architecture for hopefully future human exploration. So here's where we went, and to borrow a term from Ben Bussey, terra incognita, because it's in permanent shadow, so we have no direct sunlight that's going in here. And this is an image from the LCROSS visible camera as we're coming in and descending down towards the impact point. And if you zoom in, it's still dark. And so we wonder, why can we not tell anything that's in there? We actually have more images now of the floor, so that was a good advancement. But there was all of this controversy, scientific controversy, about what was going on in these permanently shadowed regions. And what we used to think, and what we probably, some of us have learned in classes, and some of us have taught students in classes, is that the moon's dry. We heard that this morning. We used to think the moon is bone dry. And so I just grabbed a few books off of my shelf in my office and decided to see, well, what were we saying about the moon a few years ago? In '99, the moon lacks water and other volatile compounds. The apparent lack of water or organic compounds on the moon from exploration in the 60s. And then an important unknown about the polar regions is the presence or absence of surface and subsurface ices. So we really didn't know what was going on. There were some ideas and there was some tantalizing data that was helping shape this debate, what was going on. Some of the early evidence for water was for two missions, the Clementine mission and Lunar Prospector, both in the 1990s. So Clementine had the famous bistatic radar experiment, and there were multiple papers written about how these high backscatter returns were indicative of lunar polar ice, particularly near the South Pole, so that could have been evidence for polar ice. There's also Lunar Prospector, which returned some of the first hydrogen maps, such as this one. And we heard about the land hydrogen mapping too, which is going one step further, looking at more hydrogen mapping in greater detail now. But this is from Lunar Prospector, and here you're looking down on the South Pole, and the dark regions are where you have enhanced hydrogen. It wasn't very controversial that there was enhanced hydrogen, we just didn't know what form it was, or how much it was, and the distribution at smaller scales. So these are some of the questions that LCROSS was aiming to address. So there was some evidence that maybe there's water, and then there are some other papers that said, well, maybe there's not. Here's some papers from Science and Nature saying, well, this is using Arecibo data and looking at the radar backscatter and saying, well, we see the same signature in sunlight, so maybe it's actually rough surfaces and not ice deposits that are causing this signature. And then there's another paper, no evidence for thick deposits of ice at the lunar South Pole. So I think it would be diplomatic to say that there is some healthy scientific debate over this fundamental question before we actually sent the LCROSS mission. And then there's also the question of volatiles, in addition to just water. And there are some very interesting presentations. They're all online at the LPI website from a recent conference, the Wet versus Dry Moon. Some analysis of the Apollo data showing that there's enhanced water in samples that were taken in shadow and down in little gopher holes and whatnot compared to the sunlit regions. So maybe this water story is a little more complicated than we were thinking. Water in the lunar magma ocean, so talking about early evolution of the moon, and what role did water play there. And then one of our personal favorites on the LCROSS Science team is Don't Drink the Water by Reed in '99. And it's actually a very interesting paper predicting that you should have a large amounts of mercury that are also sequestered in the poles. So be careful of the water that you're drinking. So there was a lot of work that had been done pre-LCROSS to help shape our thinking. And so then we needed to send a mission to actually answer the question. And so when LCROSS went and it flew and then we analyzed the data, LCROSS confirms the presence of water and other volatiles in Cabeus Crater, the impact site. And there's a listing of some of those other volatiles there. Down here are just images from Tony Colaprete's 2010 science paper. These are showing near-infrared spectra from the near-infrared spectrometer on board the LCROSS shepherding spacecraft. The data is in black and the model fit is in red. Showing the fits to the various different volatile compounds, and then also seeing the water bands here around 1.4, 1.8, 1.9-ish, showing this is just one line of evidence for the water. And so you can go and read the papers to get all the background information there. So the question was, as I said before, is there water in the polar regions in this particular permanently shadowed area or not? And the answer turned out to be yes, so we can all go home because now we're done. And we've answered the question and the talk can be over. But there's actually more to the story than this. So we answered that fundamental question, and now we're getting into the next level of detail, basically milking this data for all that we can to try and learn as much as possible. So what I want to do is just step through some of the findings and some of the observations that we have, and there are talks throughout the rest of the forum that will go into this in more detail. So some of the questions that we've been asking ourselves. The volatiles, okay, they're there, but where are they? Are they in the surface? Are they in the subsurface? One or the other? And so there's an observation, Diane Wooden will be talking about this in more detail, of a local regional exosphere as we're coming down from the shepherding spacecraft, making these observations of calcium, potassium, aluminum, various other entities. And so this is pointing us in the direction of believing that there are superficial deposits of various compounds in these permanently shadowed regions. So you may have a surface layer of these materials. There's water, but how deep does that water go? So looking at the plume and looking at the evolution, we have about 4 minutes of data as we're looking down on the plume and then flying through it. We see water ice very early in that plume, in the low angle plume. So that's sort of the upside down lampshade material that kind of came up in that shape and then fell back down over 50 seconds, a minute or so. So early identification of water ice grains in that plume, but then also several minutes later in the high angle plume, which is more of a jet or a spray of material that went straight up, there's also water ice in that high angle plume. And Pete Schultz and Brendan Heldmann have been doing a lot of work on the impact dynamics to try and determine, okay, where does the material from the low angle plume come from? Where does the material from the high angle plume come from? And some of their recent work is showing we would have water at depths extending down to below a meter. So not just surface deposits, but actually extending into the subsurface. And Brendan will be giving a talk about this later in the conference. So what is happening to this ice once it gets ejected up into the sunlight, both in the ejecta cloud when it's seeing the sun, and also what's going on the lunar surface. If you have ice there that's on the surface and in the subsurface, you didn't eject all of it, so what's happening to what's remaining? So over time, we see an increase in the water vapor band strength, and the OH actually transitions from fluorescence to prompt emission. And so it's not that we just see one spike, we see OH in the beginning and that's it. It's not that we just see water in the beginning and that's it. There's actually this extended source that continues over these 4 minutes. And so there must be some sort of sustained source of subliming water in order for us to see the vapor later and to see the ice grains later. So we're doing some modeling right now with our colleagues at the University of Texas in Austin, looking at the ice grain evolution as that material comes up into sunlight, and also looking at what's going on that fresh exposed crater, because there's water and there's ice that's there, and you just had this impact that came in and it heated things up, and we have thermal data to show to help constrain what those temperatures are. You probably also have chunks of warm material that have been ejected out and are now pocketing over on the lunar surface, which is also heating things up, and so we have this continued source of sublimation. And then along those lines, evidence of water remaining at or near the impact site, I'm looking at the cooling curves of the craters and doing modeling of that, what materials can actually match the data. And it's not working for just dry regolith. We actually have to have a colder we see a colder centaur floor, which is indicative of some phase change of water, so we're losing some of that energy through the subliming water that's probably that ice that's on the ground that's still left there and is subliming away because it's all been heated up, and so in hindsight that sort of makes sense. And the mechanical properties of the regolith. So one of the observations that we didn't see is a visible flash. We had a photometer that was geared just for looking at that visible flash, and we didn't see it. And in the near-infrared, there was a delayed flash, and the duration of that flash, which is leading us to believe that the regolith at that site had a high porosity. So we're not looking at just rocks, consolidated boulders, or anything like that, but a very high porosity type of regolith. So these are the types of things that we're teasing out now as we continue on. That's not to say that we've answered all the questions. There's still a whole list of outstanding questions. These are just some of them, and I'm not going to read through them because my time's running out. But we've really, I think, changed the conversation of what we're talking about in the lunar poles. We have enough information now that we can make more detailed questions, more detailed assessments of what's actually happening, and rewriting the textbooks, because before there was no water, now there is, and now it's a whole new set of questions. And so in my very last minute, I want to talk about this new paradigm. I just want to say a few words about how this mission was conducted. Because it was a pretty small, we had a shepherding spacecraft that was just basically 6 panels bolted on a big piece of metal. Low cost, under budget, under $79 million, and pretty quick in just a few years. And this enables quite a few things. One, focused, robust science and exploration objectives. You had to keep your eye on the prize. There was not a lot of room for requirements creep, and our mission management was very good at keeping us on task. And so as a result, we had, this is the science cover, and there were 6 papers about the LCROSS impact in science just last year. Also training and mission experience for scientists and engineers, and this is where I think the students can really benefit as well, because here, this is a picture of the Science Operations Center. This is Tony Colapreet, the PI, and Kim Enico, the payload lead, and there's myself back there talking to the observatories. And this is Mark Shirley, the payload lead in the high bay. Hands-on experience doing an actual real mission in just a few years, so you can actually learn something and hopefully apply that later on. And also EPO, Education and Public Outreach. This is Brian Day, who is the EPO lead for the LCROSS mission, with a bunch of students that he brought down to watch the launch, because those students actually got trained and operated this telescope to actually track LCROSS in flight, and then countless other public outreach activities that we can't even go into at this talk. So anyway, there's further talks if you want to hear more information, but I think it's been a really interesting mission, and the science continues to come. Thanks.
Jay, we've been talking for a while about the fluffy nature. Thank you. We've been talking a while about the fluffy nature of the material that the impact occurred in. Are we at a point now where we can start to constrain what those density differences are, and how much lower density it is?
Yeah, that's a good question. So what we're looking at is, for the porosity, talking about on the order of 70% or so, which is, Tony likes to refer to it as fairy castle material. It's very fluffy material. And we're also doing, in parallel with that, we're doing some modeling of what those grains look like once they've been lofted above, and looking at the color changes between what we see in the blue part of the spectrum and the red part of the spectrum. And to match those color changes with the modeling, you really need sub-micron sized particles. So there is some fraction of particles that are very, very small. There could still be a larger fraction as well, and we're constraining that right now, and also looking at the purity of the ice grains. Because in order to have ice grains lasting 4 minutes or so, which we see, you have to have a more pure type of ice grain so it doesn't sublimate away as quickly. whereas you can have dirtier ice grains, and there's been a lot of modeling for this done in the world of comets, for example, looking at how fast the sublimation rate changes as a function of the albedo of the particle. So those are the types of things that we're trying to pin down.